Like electric potential energy, voltage is not a vector. So we can add multiple voltages directly, taking into account the positive or negative sign. There's no direction here, no vectors. Like gravitational potential energy, voltage is not an absolute value. It is compared to a reference level. By assuming a reference level of voltage is equal to 0, as we do when the distance from the charge generating the voltage is infinity, infinity's a good place to have a 0 voltage, we can allow a specific value to voltage in calculations because it's being referred to a 0 voltage at infinity. Equipotential lines. They represent points in space where the electric potential, voltage, is the same, right? Equal potential. The electric potential is the same for points that are the same distance from the charge, right? What did we say voltage was here? K, Q over R. So if you have the same R for a given charge, and K of course is the constant, the voltage will be the same. So we represent them by green circles over here. And the farther you go away, the smaller the potential is. Those blue lines are your electric field lines radiating from a positive charge. The direction of the electric field lines are always perpendicular to the equipotential lines. And when we get to APC, we'll see why. The electric field lines are farther apart when the equipotential lines are farther apart. The electric field points from a high to low potential, just like a positive charge. Right? So here's your positive charge. The electric field is decreasing in that direction. And you know what? So is the electric potential. For a positive charge, like we have over in this picture here, the equipotential lines are positive and they decrease to 0 and infinity. A negative charge is surrounded by negative equipotential lines, which also go to 0 and infinity. More interesting equipotential lines are generated by more complex charge configurations, right? This is just one charge, but if we were to put a plus here, a minus here, and a plus here, you'd have to, at every point in space, add up the voltages to each one of those charges. And remember, these would be negative values, and these would be positive. And then you would connect up where you have equal potentials. So we're going to do some of those coming up. This configuration is created by a positive charge to the left, because you can see what's happening here. You start at 20 volts and it goes down to 10, then it goes down to 0. But wait a minute, this isn't infinity. No, because there's another charge. So let's say there's some kind of negative charge configuration over here. Negative 20, negative 10. And what happens in the middle is you add the voltages up due to these two charges and they cancel out and you get 0 volts. So in this case, you don't have to go to infinity to get 0 volts. You've got the effect of these two potentials canceling out right in the middle. Note the signs of the equipotential lines. Positive near the positive charge, negative near the negative, and it approaches 0. And also notice the electric field vectors. They are always perpendicular to the equipotential lines. And again, goes from positive to negative. So you can see all the arrows are pointing left to right. The work done by an external force to move a charge from infinity to a region of space with an electric potential of V has been shown to be W work equals QV. This assumed that the electric potential at infinity is 0 volts. However, in this case, we have a 0 volts right here. So what happens if we move a charge from point D on the negative 10 volt equipotential line to point B, the equipotential line for plus 10 volts? For this case, unlike the voltage at infinity, which is 0, both of these points have a non-zero value for voltage. So we need to find the change in electric potential to find the work done by an external force. So that would be Q delta V, where delta V is V final minus V initial. If we have a positive charge moving from point D to B, that means it's moving to a higher electric potential. It goes from a negative 10 to a 10, We sort of anticipate that positive work must be done by the external force, just like lifting a mass in a gravitational field. Let's see if the equation bears that out. Work is Q delta V, Q is positive, Vf minus V0. Vf in this case is 10 volts, V final is negative 10. We do the math and we get the work is 20 times Q in volts. And of course what we have here, Q is positive, so 20 times a positive number, we have positive work. What if we have a negative charge moving to a higher electric potential? In this case, we're going to anticipate negative work must be done by the external force. Let's see what happens. The equation is work equals Q delta V. We put in a minus here because it's a negative charge, and we still have Vf minus V0. Vf is 10, V0 is minus 10, so we carry out the math, and we come up the work by an external force is negative 20 Q volts. In this case, Q now is the magnitude, so it's positive. 20 is positive. This negative sign tells us that we have negative work done on the charge by the external force.